So 1.4 is totally different. Elasticity. Elasticity talks about how stretchy something is, right? In simple terms, how stretchy something is. It talks about how if you pull a rubber band and you release the force, the rubber band will always be able to return to its original shape and size. So when they ask you what is elasticity, it's the property of an elastic material to be able to return to its original shape and size after you remove the force. Okay? Your definition doesn't have to be word for word, but make sure you have those key points. And how I remember this is I would think of a rubber band every time they ask elasticity. Is that property of how the rubber band is able to go back to its original shape and size after you remove the force. Okay, after you remove the force applied. It talks about how stretchy something is. Okay, and under elasticity, there is a very important law. Important on this one, Hooke's law. Make sure you don't get his name spelling wrong. H with a double O, Hooke's law. Hooke's law says that the extension of spring, which we normally call as X, okay, is always directly proportional to the force applied, which is F. X directly proportional to F. And you think it is a very logical law. You have a spring. The more force you apply, the more it would extend, right? You have a spring and then you apply more force and then you will extend more. Very logical. Right? So they are just saying, if you apply more force, then you're going to get more extension of the spring, right? Just like that. But there is a catch though. There is this back part, provided that the elastic limit of the spring is not exceeded. So if you have ever played with you know those mechanical pencil spring, inside a mechanical pencil, there's a very small spring. If you have ever played with it before, or have you accidentally, if you have ever accidentally pulled a spring too hard that it can never go back to its original shape and size, that means that you have pulled it too hard, you have pulled it past a point called the elastic limit. Okay. Since we are talking about this elastic limit thing, I want to go and look at the graph first. This is your Hooke's law graph, very logical one. It is saying you apply more force, then you get more extension. The spring will become longer and longer and longer. Okay, extension means how much longer it becomes. You apply more force, then it extends more. You apply more force, then it extends more. Okay, but I want you all to do something. You take a red pen or whatever, you go and mark here as the elastic limit. Okay, you can mark there as the elastic limit, make it obvious. And then at the back, right, the moment you stretch something past that point, past that limit, then the line of the graph won't be straight anymore. It will become just like one. It will be like that. You just simply draw some random curly shape. But the point is, the moment that limit has been passed, it can never go back to its original shape. It will become a just spring, right? So Hooke's law is saying, yep, directly proportional and all, but only up to that point. Only this part is Hooke's law. Okay, directly proportional, provided the limit is not exceeded. Okay, only up to that point. That part is Hooke's law, behind is not. And then we go through this elastic limit part down here. Hooke's law is obeyed until the elastic limit only. But sometimes exam can ask you, what happens if you pull it past that limit? You pull it past that point. you say that the spring cannot return to its original length or shape anymore. Okay, it cannot go back to its original length anymore. It's permanently deformed, permanently spoiled already. Yeah, so there's some short stuff about the elastic limit. They can ask, I think MRSM paper or SPP paper asked before. If you pull it past that limit, what happens? You just say the spring cannot go back to its original length or shape, 1 mark, right? Okay, we look at this experiment. Last year, Selangor paper 3, they asked this experiment. So in the Selangor paper, different school, they set themselves. So some schools, they did this experiment, but not using a spring though. They did a cheaper version. They use a rubber band. Also can. Okay, they use a rubber band. Also can. So you first of all need to measure the original length, which we will normally call as the length L, but with an O, LO, original length. I can replace it with a rubber band. No problem. It works the same. Then I hang some weight on top of it. Okay. Then you get some length here. They will always ask you about this extension. This is our, this is what we want to study, the extension. Not the full length. We want to know the extension only. How much did it become longer by? How much did it extend? And you just do this with some simple maths. You take the full length minus the original length. You will then know how much it extends. Right? Simple, simple logic. Okay, and then we say directly proportional and all. So you can put X and F directly proportional. You can put F and X directly proportional. It doesn't matter, which will end up to give you this formula, which is what we call as the Hooke's law formula. It is given in SPM. Okay, you can double check at your first page there, the formula page is there. Hooke's law. Some might ask, teacher, why got a K suddenly? Have you all learned Form 5 Maths, Chapter 1? If you have, you will know that anything directly proportional, or in maths we say varies directly, if you want to put equal, you always need to put a constant there. Okay, because let's recall, directly proportional means the graph can be like that, or like that, or like that. They're all directly proportional. Correct enough. All of the 3 lines, they are directly proportional. But which one is it? So it depends on that K value, that constant. Or we call it as the gradient. It depends on the gradient. This K value is called the spring constant, or sometimes we call it the force constant. I'll talk about this later. Okay. We look at the before I move on, I want to mention one more thing. Do you notice this graph, the axis is terbalik with this graph? The X and the F are terbalik. You need to be careful because exam can give either one. Okay, exam can give either one. Just be a bit careful. I'll teach you how to see later. Okay, we look at the graph first. Normally, we will draw this graph because this graph can help us to get a few useful stuff. Okay. Can you fill in for me what is Hooke's law first? Hooke's law is F equals Kx. I'd like you to do something. Can you rearrange to make K the subject? You rearrange this formula and make K the subject. That means you move the X over and then K will be equals to F divided by X. Agree? F divided by X. Can see, yeah? Okay. And now I want to ask you, if you see a graph, do you know how to tell what the gradient represents or not? If you don't know what I'm talking about, all physics students need to know this, okay? Gradient is this. You should be a pro at this by now, okay? But when we want to talk about that physical quantity that the gradient represents, you can think of it as like this. You're taking the y-axis divided by the x-axis, which means you're taking the force divided by the extension. And we found out force divided by extension is the same thing as the K. Okay, so your gradient of this graph is actually the y-axis on top, x-axis at the bottom, which is the same thing as the spring constant. Always remember, the physical quantity represented by gradient is always y-axis over x-axis. y2 minus y1 on top, y-axis on top, x-axis at the bottom. Okay. And then this one is something new. The area underneath the graph. We learned before, a graph, you can look at it as, you can go and find gradient. The gradient normally means something. The area also normally means something. And the area underneath here, they say, is the elastic potential energy. It represents the energy. It's a triangle, half times the base here, x, times the height here, f. Or you put f first also can. Okay, so we know, or normally we say elastic potential energy is, okay, usually we will put E to represent energy and the little p to represent the potential energy, half Fx or xf lah, up to you. Can you go and sub in something? If I sub the f away, I want you to see this formula can also look like another version. Okay, I just sub the f away. F become kx already. Then you get half kx squared. The first three subtopic got no formula at all. You're just doing F equals MA, right? Now the fourth subtopic, 1.4 elasticity, suddenly got a few formulas. Do I need to memorize any of them? Don't need. They are all in the formula sheet. Okay, you can refer to your book, first page. It's all here. Hooke's law is there, number one. Number two, elastic potential energy. Number three, also elastic potential energy. All given. Don't need to worry. Okay, can I ask you something extra? So remember I talked about how sometimes exam want to trick you. They swap the x and y axis. What if I put f here, x here, and I go and draw the same graph? The graph will have a similar shape also. It's also directly proportional. Okay. Now the question will sound like this. How can you get the gradient from that graph? How to get the gradient? Sorry. Let me rephrase again. How to get the spring constant? My bad. How to get the spring constant from that graph? Okay. The gradient of this graph is going to be f over x. Okay, this is extra. Right? The grade. Hey, sorry. Y-axis on top, x-axis at the bottom. My bad. Okay, like this. That's the gradient of this graph. Okay. But spring constant is like this. How to make it look the same? You just go and terbalik this. You see, this is on one side, it is the gradient m over 1. On the other side is x over f. What if I just terbalik both sides? I can do that. And it is now the spring constant. So it is not impossible to find the spring constant if they switch the axis. You can. You just have to do 1 over the gradient. Oh, sorry. Yes, please point out to me if I make mistake. Sorry. I was saying, my bad. Sorry to confuse you. I terbalik both sides. So here is f over x. Yes. Thanks, Brian. Yeah, m over 1, x over f, both sides terbalik. And after I terbalik, it becomes the spring constant already. Okay, so I don't want you all to think, hey, if they change the axis, it's the end of the world, you can't do it. You can. Just maybe need to do an extra step. Okay, then I explain to them, I say the question, in order to get the spring constant, I'm going to do 1 over of the gradient of this graph. Okay. Next page. The meaning of elastic potential energy. Different from elasticity. This is talking about energy. So you start with the word energy. It's the energy that you get when you go and pull a spring, or when you go and compress a spring, when you go and stretch or compress something. Okay, it's a kind of energy. So you start with the word energy when you stretch something or you compress something. This definition not that popular. The most popular one so far is Hooke's law. Hooke's law must know. Hooke's law is popular. So I put star here. Okay. And then I want to revisit again some formula. So far, I feel every physics student needs to know this. Gravitational potential energy. This. Okay. You might need to use this later on. Kinetic energy, we will use quite a bit later on in Form 5. Today we learn these 2 new ones. And don't forget, this one we learn in Form 4, Chapter 4. When you learn about heat, right? Electrical energy is equals to the power times the time. Sometimes they might give you in this form. Q stands for heat energy. But think about this. These two can be interchangeable because normally, how do you get heat? Let's say a rice cooker. You plug into the electricity source, then the electricity becomes heat, then cook the rice. Right? That's why we can change the 2 symbols. The energy can also become heat. Yeah. So this is the version that you might see in the formula sheet. They are the same. You will see this again in chapter 3 later, when you learn about the chapter electricity. Okay. This very important. Later, this one also very important. The meaning of the spring constant. Whenever we say high spring constant, that K means spring constant, or sometimes they call it force constant, you must always remember it means that the spring, number 1, is stiffer, or you can use the word harder to describe it. A very hard spring. But it also means that a hard spring is less elastic. And if something is less elastic, something is very hard to pull or compress, it will give you very small extension. When you pull it, it doesn't get pulled too much. Smaller extension or smaller compression also. Which is the XR. But a very good thing about high spring constant, right, is that it can support more load. It can support more force. It is stronger. All of these things, they all mean higher spring constant. So now you ask me, in SPM questions, do we normally want to prefer to pick something that is higher spring constant or lower spring constant? Almost, okay, 99% of the time, we always want high spring constant because it is stronger, because it can support more load. And I can give you in a lot of application, for example, the springs in your bed, the springs on the sofa, the springs in the car, so that the car doesn't bounce too much, right? On the sofa, on the bed, on the car, on the motorcycle, all of it, you want it to be stronger. You don't want a spring that if somebody sit down on the sofa, immediately it breaks or immediately it cannot withstand the force, right? You need to carry someone that is 50, 60, 70 kg on the sofa. You need to have a very strong spring. Therefore, it has to be harder, stiffer. Yeah, lah, maybe a bit less comfortable, but no sofa is like sponge soft one, right? It's quite firm usually. Okay, so it has to be strong. It cannot be too soft. Yeah, usually exam will ask you to get something that is high spring constant. Why I say this yellow table important? Because this can come out in essay. And if it comes out in essay, I think it's very easy. Let's see. They say, circle the characteristics of a spring that will give higher spring constant. You take a pen that is more obvious, okay, and make sure you circle the correct one. You can use a red pen if you want. Make sure you circle the correct one because you're going to read this. If you circle the wrong one, you're going to read the wrong thing. We start with steel versus copper. Which one do you think is stronger or harder? Steel, because steel is an alloy, right? Steel is an alloy. Yesterday, somebody said copper, right? That means your chemistry a bit shaky if you pick copper. The reason why we create alloy is what? Alloy is what? You mix an original atoms of something and then you add on some atoms, right? What's the point of doing that? To make it stronger, to give it better properties. Okay, and one very good grade of steel that we see a lot in our daily life is called stainless steel. Okay, it's a very good grade steel, doesn't rust easily. So steel, copper, I will pick steel. Okay, length. Which one do you think is harder to pull? Do you think a very short spring is very hard to pull? Or do you think a long spring is harder to pull? The shorter one. The shorter one. The long one easier to pull one. Okay, if it's a long spring, it's easier to pull one. The shorter one a bit harder. And anything harder will have higher spring constant. Next one, thickness of spring wire. This one we are talking about the wire. So like this versus a thin wire. Like okay, the length, everything the same. Just one very thick, one very thin. Thicker one for sure, harder to pull. Okay, last one. Diameter of spring. Diameter is talking about this diameter. Okay. Do you think a bigger diameter spring is very stretchy? We want a less stretchy one. So do I pick the small one or the big one? Yeah, if it's very big, it's very easy to pull one. If it's very small, it is very hard to pull, harder to pull. Small diameter spring gives you a higher spring constant. Okay, and I can think of a essay question at the top of my head. It sounds like that. Last year, if not mistaken, Pahang paper. This year, the latest Pahang paper, they asked something like this. Design a spring system for your sofa, for example. Okay, I want the sofa to be able to withstand more load. Well, I will pick a steel spring, a shorter spring, a thicker spring, and a thicker spring wire, and also a smaller diameter of spring. 4 marks already. What's the reason? I will say, because it will give me higher spring constant. That's 1 mark. You can say that. It is a harder spring. It can withstand more load. It is stronger. That is another 4 marks. So all of this give you the same reason one, right? Reason can be repeated, no problem. In total, 8 marks already. 8 marks already. For modification, and then your reasons on top. Why do we want high spring constant? Okay. Or the reason could be because it is high spring constant, that's why you pick steel, for example. Can also. Okay, so this one important for essay. Later got one question I included. Okay, one last part. And then I think that's all that I want to teach. The last part is arrangement of the spring. Okay, so we talk about a spring, and if you put two springs connected at the end like this, we call it a series arrangement. If you put it side by side, we call it a parallel arrangement. Okay, someone asked, what if all four also write higher spring constant? Cannot. I want to say can, but I also don't want to say that. If you know got other reasons, you try to write other reasons lah, right? But it's not wrong lah, actually. It's not wrong, actually. Okay, it's a very hard question to answer. It really depends on the examiner, actually. I've seen marking scheme that write high spring constant all the way before. I have. But they will also slash other answers. Okay, can support more load. It is stronger. It is a harder spring. It is stiffer. Yeah. Okay, so back to here, series and parallel. Okay, maybe I put some force lah. Let's say here I put 10 Newton. 10 Newton. If I'm pulling the system, the spring system, with 10 Newton of force, I think you would agree that this spring would also withstand 10 Newton. This spring also 10 Newton. Right? However much you pull, each one will withstand the same amount of force. But if you put parallel arrangement, then it will share. It will be half the force, half the force. Yeah, if each spring experience more force, it will extend more. If the spring only experience 5 Newton, it will extend less. It's a very simple logic. It is Hooke's law. You pull more, you get more extension. You pull less, less extension. So you just have to check how much is it experiencing. Is it 5 or is it 10? Okay, which is why you see here, if the force is F, the tension that it experiences also F. If it's 10, it's all 10. But if here's F, here would be half of F. Right? If it's 10, then share, it'll be 5. Okay. Then extension also same lah. Each one will extend by X. But then this one, each one will extend by half of the extension only. Okay. So it's a simple logic, I feel. You can write down here. This one, you have the same load that is applied to each spring. However much you pull, all the spring would experience the same force, the same load. But then this one, if it's parallel, we say that the load is shared equally among the springs. I feel quite logical. I don't really have to memorize or anything. Okay, then we look at the series one first. Tension of each spring is just F. You pull F, then it will all be F. The extension of each spring will be X. The total extension of the of the entire spring system is 2x. One spring extend by x, the other one also x. So in total, 2 times of x. So that is for 2 springs. If 3 springs, 3 times of x. 4 springs, 4 times of x. If it's n number of springs, n times of x. Yeah, if it's 2, then 2x, 3, then 3x, 4, then 4x, then n times of m number of springs, then n times of x. Okay, the other one, parallel arrangement. Your tension in each spring, the force will be shared lah. So extension also will share, will be halved. I don't need to extend so much because I only experience 5 Newton, not 10. So when we look at the entire system, right, you don't go and add half. You don't say, oh, here half, there half, total become 1. No. We look at the entire thing, the entire diagram only stretch or only become longer by half x. The answer is just half x. Okay, you look at the whole picture, the whole system. You don't need to go and add it up. And then if you have 3 spring, then divide by 3. If you got 4 spring, then you divide by 4. If you got n number of springs, then you divide by n. Okay, before you move on, can I talk about 2 things here real quick? For series arrangement, spring constant, which is your K, is smaller one. For parallel arrangement, the K is bigger. Yeah, so some people would think, I realize a lot of Form 5 students towards the, like when I do trial paper practices at the end of the syllabus, they always get confused with this sometimes. They'll think, hey, spring constant is for the spring, why you talk about the whole system? I'm talking about the whole system. For this entire series system, the series one is easier to pull. The series one is easier to pull. Yeah. And if the system is easier to pull, automatically spring constant will also be small. But if you look at the parallel system, if it's harder to pull because so many springs is holding onto it, then the K value of the whole system will also be bigger. I can talk about the entire system one. It doesn't always have to be one spring like that. Okay, we can talk about the whole thing. Yeah, so parallel arrangement, harder to pull, then K value bigger. K value big is always talking about harder to pull, stronger spring.